Welcome back to today's lesson. Today we'll be covering on matter. Matter is something that you can find in your periodic table. It exists as a form of element. It exists as a form of atom being surrounded by C or delocalized electron. It also can be existing in a form of alloys. Alloys is what we call where you have metals mixed with other metals or metals mixed with other elements or atoms. So before the metal is being mixed to form alloys, this is the structure. It's orderly and it's neat. Hence, it's very easy for you to push them apart, to slide them through. However, after you mix the alloys, mixed with other atoms to form alloys, you actually expect to see that other atoms or other molecules, other atoms will actually have different in sizes, and as a result of this difference in sizes, you're going to disrupt the orderly arrangement. See, the keyword here is disrupt the orderly arrangement, hence making it harder for the person to push through. As a result, alloys are usually much stronger than the metal itself. So now I'll move on to the main part of today's chapter, which is on the reactivity series. You have to know the reactivity series at your fingertips, because a lot of the subsequent parts in this chapter requires the knowledge of the reactivity series. There's a lot of ways that you can come up with acronyms to remember the reactivity series. Personally, for me, I prefer using this. You can use this too. Please send cats, monkeys, and zebra in large hydrogen cages. So you have sodium, you have potassium, sodium, calcium, magnesium, aluminium, zinc, iron, lead, hydrogen, copper, silver. So the reactivity decreases as you go down this table. So once you have familiarized yourself with this series, we can move on to the important things. The first important things that you need to know for this chapter. You need to know that matter is able to react with water. Once matter reacts with water, you will expect to produce a metal hydroxide plus H2 gas. And matter also can react with steam, which is a more energetic form of water. And you will expect to produce metal oxide and H2 gas. Remember, this reaction is very explosive because of the presence of H2 gas. The moment you know that there's H2 gas, you're going to expect a certain level of explosion or a certain level of danger involved in this experiment. So looking at the reactivity series, the first three is very reactive with water. They react very violently. The subsequent ones, they react with hot water or steam only, and they react very slowly because they are not as reactive as the first two. And the last few after iron will totally not react with water at all. So now we'll move on to the next part, which is on acid. As we learned previous chapter, metal will react acid to produce salt and H2. As you know, H2 is explosive. That means you expect the reaction to be actually very violently or vigorously. So the first few reacts all the way until iron, and subsequently from lead, copper, silver onwards, there will not be reaction. And of course, the level of intensity for the chemical reaction also depends on the reactivity of the metal itself. Now we will move on to the third things that you need to know. The third thing is that you must know that metal oxides can be reduced by carbon or H2. If you are reduced by carbon and H2, for carbon you expect to get a metal as a product and carbon dioxide. And for H2 you will get metal plus water or steam. The first few has totally no effect because they are very strong. So if you are a very reactive metal, you will tend to make a very strong bond between the metal oxides. And as a result, it's very hard for you to actually separate them apart. So the first few has no reaction. For zinc, can be reduced by carbon but cannot be reduced by H2. And subsequently, they all can be reduced by carbon and H2. And even the last few, which is super unreactive, it's so easy to break them apart. It just decomposes by basically you hitting A. Now we will move on to the fourth part, which I think is very important, is that you must know that a more reactive metal has the ability to displace a less reactive metal from its metal oxide or from its salt solution. So let's look at an example. When you react iron with copper sulfate, you expect to get copper and iron sulfate, iron 2 sulfate. So of course, in the exam situation, they will not just ask you how to write the equation, they will also ask you about the observation. So the observation is very straightforward. Copper sulfate is blue color. So initially it's blue. The blue slowly begin to fade and becomes green, and you expect a reddish brown deposit form in the solution. Now we will move on to the fifth part, which I think is very important, is that heating a metal carbonate will result in getting you a metal oxide plus carbon dioxide. The first few has no effect, which is potassium, sodium. Subsequently, they will have effect. And the last one is very straightforward. The moment you heat, it decomposes. And for the next part, which I think is the most important part in this chapter of iron, is that you must understand how blast furnace works, how iron is being produced, and how that iron is eventually being produced and converted into steel. So let's first understand how blast furnace works. Blast furnace is an industrial method of making iron. It has been used for thousands of years, or for hundreds of years. In fact, for hundreds of years. In fact, it's still being used currently in today's industry. For this, you need to have three starting material. Of course, you need iron. However, in the earth crust, the only way you can get iron is that you will get iron in the form of iron ore, which is known as hematite. So basically, people go mine it and they will expect to get hematite, which is Fe2O3, iron 3 oxide. And the next ingredient you're going to add is limestone, which is calcium carbonate. And the last ingredient you're going to add is called coke, which is carbon. And sorry, not forgetting that you still need one more ingredient, which so-called is an ingredient. You need the presence of air. So you need to pump in air. You will find out the reason why later on. So the key step, there's a few equations that you need to memorize or familiarize yourself with. However, I usually teach my students to actually go to a key step. The key step is that you want to get iron. So how do you get iron? The iron ore actually is being reduced by carbon monoxide. Sorry, there's a mistake here. The iron ore is actually being reduced by carbon monoxide to actually give the iron and the carbon dioxide. However, this iron here is actually an impure form of iron. So it's still very impure. That means there's other mixture inside this iron. However, you're already separated from the oxygen. So the key step here is to actually get the carbon monoxide. Of course, in air, there's no carbon monoxide because carbon monoxide is a harmful gas. So how can we produce carbon monoxide? We use coke. Coke will react with oxygen, which you can find in the air, to produce carbon dioxide. Then carbon dioxide is being reduced by coke again to produce carbon monoxide. And this carbon monoxide is used to reduce the iron ore to produce iron and carbon dioxide. However, this iron is impure, so how do you remove the impurity? You use the limestone. The limestone, when you add it in, it will decompose due to heating, which we previously covered here. And you'll form a calcium oxide plus carbon dioxide. The calcium oxide is then reacted with the impurities, which is silicon oxide. Silicon oxide is what you commonly know as sand. Yes. So it reacts with silicon oxide. And once it reacts with silicon oxide, you produce calcium silicate, which is a slag. The slag, the molten slag, can be used for pavement of roads. It floats on top of the molten iron. The reason is because you do not want the iron to be oxidized, so there's a special property, which is that it's less dense, hence it can float on top. So once you remove this, the iron you get is called pig iron, which is quite pure. However, for further step, which you want to convert into steel, you're going to put it into another furnace. You're going to pump in pure oxygen to remove the carbon, which is the coke, excess coke, and sulfur. There will be some presence of sulfur. There will become carbon dioxide and sulfur dioxide, and you escape off as gas. Then next you add limestone to repeat this same process again to remove the unremoved silicon oxide, and you will change into slag, and you then can remove it naturally. And the last part of it, to make steel, you have to add carbon, because adding carbon, you're going to make it to become a form of alloy, and carbon makes it strong. By adding higher percentage of carbon, I mean high as in a few percent, not as in 90%. So as relative high percentage of carbon, you're going to make the iron become very strong and brittle. This is called high carbon steel. If you add low percentage of carbon, you're going to make it soft and malleable. That means soft can bend and malleable. So of course they are used for different property. For the soft and malleable is used to make car, and the strong and brittle is to actually construct. And the last type of steel is for stainless steel. Stainless steel add a certain percentage of chromium, a certain percentage of nickel. And stainless steel, as it suggests, it does not rust. So now we'll move on to the last part of metal, which is on rusting. So we know that metal rusts over time. If you look at a piece of metal, after a while, you will see a brown coating over it. That is the reason is because it has formed a certain level of, it has formed to its metal oxide. Because once any form of metal rusts, it becomes an oxide. So remember, only iron rusts. The rest we will use the word corrode. It corrodes. Other metal corrodes, sodium corrodes, magnesium corrodes. We do not say magnesium rust, only iron will rust. And remember, for corrosion to occur, you need two things to be present. The first is water, second is oxygen. Without these two, this process cannot occur. So with only water, without oxygen, there's no rusting or there's no corrosion. With only oxygen, there's no water, it will not happen. However, there's ways that humans can actually prevent it and has been already thought of. So the first way is very common sense. You coat it with a layer of plastic, for example. You cover it with a layer of plastic so that it's not exposed to the oxygen or the water in the air and in moisture. Or you can actually coat it with a coating, a certain coating. Or the very unique way is actually galvanize it with a certain layer of metal. Or alternatively, you can use this method called a sacrificial protection. Sacrificial protection means that you connect or you touch a piece of metal that you want to protect from rusting, such as, for example, iron, with another piece of metal that you don't really care. It doesn't matter to you. But however, this piece of metal is much more reactive than the iron itself. So you touch both of them together, connected, and as a result, after some time, you realize that the more reactive metal tends to rust over the less reactive metal, because the more reactive metal is more electronegative, hence it has a higher tendency to rust. Basically, rusting is to just changing it from iron to Fe2 plus or Fe3 plus. So talking about which one has a higher tendency of losing the electron. So more reactive metal has that tendency. So as a result, you replace the less reactive metal. Or the last part of it, you can make it an alloy, as you say, like for example, in the example of stainless steel. So with that, I have come to the end of today's lesson. Please do your revision and stay tuned. Thank you.